Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon or good morning, everybody. My name is Sergio Panetta, and we're going to discuss neutral grounding resistors, how to size and how to specify. First thing I'd like to discuss is the applicable standards involved for neutral grounding resistors. Everyone's heard of IEEE 32, the original standard on the requirements, terminology, and test procedures for neutral grounding resistors. That was recently superseded by IEEE C57.32, which was published in 2015, IEEE Standards for Requirements, Terminology, and Test Procedures for Neutral Grounding Resistors. And those of you in Canada, there is CSA C22.2 number 295, published in 2015, specifically for neutral grounding devices. As well, there's a new standard in IEC under the transformers, IEC 60076, Part 25, which will be for neutral grounding resistors. And that will be published probably within the next 2 or 3 years. There's a couple of terms we have to go over before we get started and get into this. The rated voltage, rated current, rated time, which is typically what people specify when they have a resistor. So it's not uncommon to have a 8,000 volt, 400 amp, 10-second resistor. What's implied when you say that is the maximum temperature and the temperature coefficient of resistance. And we're going to touch on all these terms so that you better understand them when you are specifying neutral grounding resistors. The rated voltage, first of all, since the active material used in a resistor has an appreciable temperature coefficient, remember that was the part that we did not specify in the requirements, a resistance is materially changed during the time of operation, causing the current to decrease. So what basically happens is the temperature coefficient of resistance changes the value of resistance in your NGR such that it increases over the temperature range. And we're going to touch into that a little bit later. When the product of the fault current and the resistance at 30 degrees C exceeds 80% of the line to neutral voltage, the resistor shall be rated for constant voltage at the rated voltage. Typical resistors are always going to be rated for the line to neutral voltage. If you have a 600 volt system, your rated voltage is going to be 347 volts. If you have an 13.8 kV system, your rated voltage is going to be 8,000 volts. Basically, with that information, we can get into the testing. So there's 2 types of dielectric strength tests that have to be done on a resistor. And these are the values that compare IEEE C57.32 and CSA Part 295. So you can see at 480, the voltages are the same. The test voltages are the same, because basically what we do for high pod is we take twice the rated voltage plus 1 kV. Where they start to differ is above 1,000 volts. IEEE C57.32 says that you need to high pod or apply a dielectric strength of 2.25 times the rated voltage plus 2 kV, whereas CSA 295 has specific ratings, 5, 15, 19, 26, depending on the rated voltage of your system. So you can see there's an appreciable difference here. Part of my understanding is if you buy a resistor in the United States, they're going to follow C57.32 high pod values. And if you buy a resistor for Canada, and if it's approved to CSA C295, you have to apply this test voltage or a dielectric strength. The rated current is not what we expect it to be. It is the initial current through the resistor. Remember we said earlier that the rated, the temperature coefficient of resistance materially changes the resistance value of your resistor. So the rated current is only the initial current that we first limit the fault current to. And then the resistance is going to increase, thereby reducing the current at the end of the temperature range. Rated time shall be 10 seconds, 1 minute, 10 minutes, extended time, or continuous duty. Continuous duty is also the steady state duty. So the extended time shall not exceed an average of 90 days per year. And the extended duty is basically a continuous duty, but you're allowed a higher temperature rise for the extended duty. And these are for unmanned scenarios. So here's where we get into some issues. 10-second and 1 minute rating resistors. The 10-second and 1 minute device is taken as the sum of the steady state rise and the additional rise caused by a rated fault for rated time. So for example, if you have a 400 amp 10-second resistor, that resistor is going to be rated for 400 amps 10 seconds. But you can also have a resistor rated for 400 amp 10 seconds and 80 amps continuous. We don't have two different types of resistors in there that change the value. The final rating of that resistor is going to be 400 amp 10 seconds, but it can tolerate a continuous temperature, a continuous current rating of 80 amps, so that when you add the temperature rise of an 80 amp unit, and then you get hit by a fault for 400 amp 10 seconds, the maximum temperature rise shall not exceed the limit for that temperature, for that resistor, and for that rated device. So you have to sum the continuous current temperature rise and the actual applied fault current temperature rise, and those values cannot exceed a certain value. A 10-minute rated resistor is taken as the sum of the steady state rise specified, otherwise it's zero. Remember, if you don't specify the continuous current rating, it's going to be assumed to be zero. And this becomes important later when you start paralleling resistors. So it's basically the same thing as a 10-second, only we have 10 minutes. Extended time ratings is it's a steady state continuous rating at a known current, but your temperature rise is going to be different. And we're going to get to what the temperature rise is later. The steady state time rating is the rated temperature rise of a steady state device, and this is a continuous rated device. So if you have a 5 amp continuous resistor and you apply 5 amps to it, through it, the temperature rise will never exceed a certain level. Those levels are here. For a steady, these are all hotspot temperature rises. So you have to keep in mind, they're not averages. A hotspot temperature rises, we take what we assume to be the hottest spot in the resistor and we monitor the temperature. An average temperature rise is that you're allowed to actually check several spots on the resistor and average them out. So what some manufacturers do is the thermocouples on the top of the resistor and a couple of thermocouples on the bottom of the resistor, and when you average them out, you get an average. That's not the case. The hottest spot is where you monitor the temperature. So IEEE C57.32 has a hotspot steady state rise of 385 degrees. So if you have a 5 amp continuous resistor, the temperature rise is 385 degrees C above ambient. Whereas if you follow CSA, it's 375. These are not different numbers. The difference between these two numbers is the IEEE ambient temperature is 30 degrees C And the CSA ambient temperature is 40 degrees C. So the final temperature on the resistor is going to be the same. The temperature rise is a little bit different. So 385 over 30, 375 over 40. Extended, 610 degrees C above an ambient of 30, or 600 degrees in CSA above an ambient of 40. 10-minute rated resistor, same as the extended time, but less than 10 minutes is 760 degrees C above an ambient of 30 under IEEE C57.32, and 750 degrees C above an ambient of 40 for CSA. And remember, these are hotspot temperatures. Sorry. So the temperature coefficient of resistance, and I know we've seen these terms in CSA, or sorry, IEEE 32 and IEEE C57.32. So alpha is a temperature coefficient of resistance, and it's expressed in 1 over degree C. What it basically tells you is there's a somewhat linear proportion of a resistance change per degree change. R2 is the final resistance of your neutral grounding resistor after rated time and rated current. R1 is the initial resistance rating, and for more often than not, that's going to be at ambient temperature. Theta 2 is the final resistance. Theta 1 is the initial resistance. Or sorry, I apologize. Theta 2 is the final temperature. Theta 1 is the initial temperature. This can be expressed as the final resistance is equal to 1 plus alpha times the temperature rise. Why that's important is because the temperature coefficient for different materials is different. Stainless steel 304 has a temperature coefficient of resistance of 0.00092. 430 stainless steels have a temperature coefficient of resistance of 0.00146. 18SR is 0.000358, and 1JR is 0.00024. These all seem like relatively small values, but let's try applying these values and see what happens on a resistor. So for example, we have a 347 volt 5 amp continuous resistor. We know the rated voltage is 347 volts. We know the rated current is 5 amps. Rated time is continuous, and from the standard, we're going to use 385 degrees C temperature rise as a maximum that we can possibly have. You can certainly choose a lower level, and sometimes we do choose lower levels of temperature rise if the resistor is going to be put in a hazardous location and we can't exceed the ignition temperature of certain atmospheres. So as a consumer, you can specify what the maximum temperature rise is to be. The temperature coefficient of resistance is not specified. So I, as a manufacturer, will test elements. I will put 5 amps of current through each one of these 5 elements, and I measure the temperature rise. When I get to a value that's closest to the limit of 385 degrees Celsius, element number 5 is the best element I can choose to fulfill that 5 amp continuous duty. But that element could be made of the 304 stainless steel, 430 stainless steel, 18SR stainless steel, or 1JR stainless steel with the following corresponding temperature coefficient over degrees C. With a 35 degrees C temperature rise, and we start with a 69.4 ohm resistor, which is basically 347 volts divided by 5 amps. Alpha is this number here. We can calculate what the final resistance is. The final resistance in this scenario is 35 increase, so 69.4 ohm resistor at the elevated temperature of 385 385 is 93.98 ohms. 430 stainless steel, 56% increase in resistance to 108.41, which is a decrease of 36% of current to 3.2 amps. A 9% increase to 75.8 ohms, or less than a 10% decrease in current. The first two rows violate CSA. One of the clauses in CSA is that when we apply rated voltage to a resistor, and when we take off that current, the resistance decrease here with the increase with 430. These two elements would satisfy the CSA requirements. We have another example, 2400 volt, 400 amp, 10-second resistor. Rated voltage is 2400 volts. The rated current, initial current, 400 amps. There is no continuous portion specified in this example, and the rated time is 10 seconds. That implies the maximum temperature rise is 760 degrees C, and a specific steel is not specified, and all manufacturers do the same thing. You put 400 amps in 10 seconds on a element, and you capture the maximum 60 degrees C. You cannot use element 6, but you can use element 5 because it comes close to the 760 degrees C temperature rise in 10 seconds. So element number 5 is suitable. 4, 3, 2, and 1, probably overkill, and you end up with too much mass as a neutral grounding resistor. Again, 2400 volt, 400 amp, 10 seconds is a 6 ohm resistor. R1 is 6 ohms. 760 degrees C is the temperature rise. So using the same formulas we had before, we can calculate the final resistance, and we get 304 stainless steel increasing 70% to 10.2 ohms, which results in a 41.1% decrease from 400 amps to 235 amps at the end of 10 seconds. 430, 110 degrees, 110% increase in resistance to 12.65, which results in a greater than 50% decrease of current from 400 amps to 189 amps. 18SR, 27% increase, 21% decrease to 314, and 1JR, 18% increase to 7.1, which is a 15% decrease in current. The first three rows do not correspond with CSA 295, as the current decreases more than 20% at the end of rated voltage being applied. The first two rows violate C57.32 as the resistance increases by more than 67%. So there's a suggestion in C57.32 that says that the resistance should not change by more than 67% of the rated resistance. But here's a good one. So we're going to have 2400 volt, 400 amp, 10-second resistor with a portion of continuous current going through the resistor. This becomes really important when you have paralleling generators and you put a resistor on each generator. There's going to be a certain degree of circulating current going through the resistor even when there is no fault on the system. This is due to the Differences in pitches of the generators, or if you have a generator in parallel with a transformer, because you have dissimilar pitches, you're going to get circulating currents, and that circulating current is going to be the continuous current portion of the resistor. So we know the rated voltage is 2400 volt, rated current is 400 amps, 20 amp continuous. The rated resistance for this particular device is 6 ohms. We know that it's a 10-second rating, so 760 degrees C above ambient, and the temperature coefficient of resistance is not specified. The first thing the manufacturer is going to do is he's going to determine the temperature rise of 20 amp continuous through a resistor. So this is the same element. We're going to put 10 amps of current through here, 20 amps of current, 30 amps of current, 50 amps of current, 100 amps of current, and we're going to measure the continuous current portion of element X. And we're going to find that at 20, so we can choose 170 or 225 degrees. That's going to be our base temperature. So one temperature rise to the neutral grounding resistor is going to be 225 degrees. Now we have to apply the maximum temperature rise of 760. The initial current of 20 amps produces a temperature rise of 225 degrees C. The initial current and the temperature limits gives us 535 degrees C temperature rise for the 400 amp 10 seconds. Now we're going to pass 760 degrees C. Our new temperature rise limit is going to be 565 degrees C. And we can see that if you pass 100 amps of current through this element, we're going to get a temperature rise of 225, 200 amps. What's important here is the 400 amps. The 400 amps is going to have a temperature rise of about 500 degrees C. So the sum of the temperature rise due to the steady state temperature current of 20 amps is 225 degrees C, and the full current after 10 seconds is an additional 500 degrees C. We sum those two temperatures together according to the rating of a 10-second resistor, taken as the sum of the steady state rise and the additional rise by the application of rated voltage for rated time. The sum of those two temperatures or currents is 725 degrees. You can use this element for that specific rating. There's no rule of thumb that says a 400 amp 10-second resistor can tolerate any percentage of continuous current. That's going to vary from manufacturer to manufacturer because we all have specific elements that we use. So when we get to the final temperature, after the initial current of 20 amps continuously, we get a maximum increase of 20% in the resistance. So we drop the currents respectively from 17%, 25%, 7%, and 5%. The second one here violates CSA 295 because our current decreased by more than 20%. So we have to rule out 430 right away. At the end of the time, 20 amps continuous and then 400 amp 10 seconds, we get the same values that we had before. First three rows violate CSA because the current decreases by more than 20%, and the first two rows increase the resistance by more than 67%, so they violate that standard as well. So when you apply a neutral grounding resistor to a specific system, we have what we have called the capacitive charging current. And the capacitive charging current is a measure of how large your electrical system is. Every conductor in your electrical system has a potential to ground. So you have basically one potential in your conductor, an insulating medium around that conductor, and then a ground plane usually on the outside. So it could be laying in a cable tray, it could be laying in a conduit. So you have two potentials isolated by a insulation medium, and that's called a capacitor. So we have distributed capacitance. What I've done here is I've drawn the capacitance as a lumped capacitor so you can see how it works, and not distributed capacitance, but it's actually distributed capacitance. The rated voltage to ground in this system is, let's say it's 347 volts. So 347 volts from A to ground, B to ground, and C to ground. The corresponding capacitance is 90 degrees leading the voltage. So the corresponding capacitance of I is this value here, B and C. And when you sum those up, if you're going to put a zero sequence CT, no, let me see. Bear with me one sec, I gotta get my pen. If you're going to put a zero sequence CT right here, you're going to measure zero because all those currents return back to the source through the other phases. One misconception that people have is the capacitive current does not return back through the resistor. This is wrong. The capacitive current comes down A phase and returns on B or A phase or C phase. It does not return back through the neutral. When you have a fault on the system, and here's our fault right here, we faulted A phase. So we have three paths of current for the three fault paths for the current to take back to the source. We have a path of current going through this method, a path of current going through this method, and a path going through the resistor. One of the requirements for a high resistance grounded system is the fault current, the resistive current, has to be equal to or greater than your capacitive current, total capacitive current. And your total capacitive current is here, and it is the sum of the C phase current and B phase current when you have a fault on the system. There's a couple ways you can measure capacitive charging current. One is to actually place a fault on your system and measure what the fault current is and subtract it from the resistive current, and the difference of those two squared values, the square root of that, equals your charging current. If you have an ungrounded system, placing a fault on the system and measuring the current here at the fault measures the capacitive current. You can calculate what the capacitive current is, and there are some programs that allow you to do that. So here we have the fault current. So let's say, for example, we have a 5 amp fault, and our capacitive current is 5 amps. That means we have a total fault current of 7.07 amps. So again, in an effective high resistance grounded system, the resistive current has to be greater than or equal to the capacitive charging current of the system. If the resistive current is less than 10 amps, and if your rated is less than 5 kV, CSA says that you can keep your system operational without power interruption, and Z462 and 70E say that you have an arc flash mitigation technique. If your rated voltage is greater than 5 kV, you have to look at the insulation levels. So if your insulation level is greater than 5,000 volts and your ground fault is on the system for less than a minute, you can use 100% rated insulation. If your ground fault is on the system from 1 minute to 1 hour, you have to use 133% rated insulation. And if your fault is on the system for greater than 1 hour, you have to use 173% rated insulation. But again, this only comes into effect above 5,000 volts, not 4160, not 5 kV, but 5,000 volts. Below 5,000 volts, it's not really a concern because the insulation around the cables ensure that they're there for more mechanical strength than electrical strength, so that you are protected. So if you have a resistor and you connect it to the neutral, the resistance value is basically equal to the rated voltage, line to neutral voltage, divided by the current. The fault current always has to return back to the source. You can use a step-down transformer and a resistor coupling the secondary so that you limit your fault current to the turns ratio squared times the voltage to neutral and the current. And the fault current goes back this way. We can use a zigzag transformer when you have a delta system here. Here we have a delta system. Or what I like to use this is when we have multiple sources. We can have multiple generators connected together and connect the entire system through a zigzag transformer. And then when we have that, we can actually limit our fault current to a known value, irregardless of how many generators are online. So if you had a medium voltage system and you had a 400 amp resistor on each of 3 generators, if all 3 generators are running, you have a maximum ground fault current of 1200 amps. If you have 2 generators running, 800 amps of maximum ground fault current. Same thing if you had a fault current on low voltage of a 5 amp resistor on each generator. And when all 3 generators are running, that's basically a 15 amp current. Now 250.36 in the United States says that you can have a high resistance grounded system up to 1000 volts, and if you limit the fault current to a low value. CSA 10-300 says that if you have an impedance grounded system up to 5 kV, you can limit your fault currents to 10 amps and less and not isolate. However, if you have 3 generators and each one of them limit the fault current to 5 amps, that means you're going to have a maximum fault current of 15 amps and you have to trip. There are ways around this, and we're going to get to that later. But the benefit of using a zigzag transformer as opposed to the other 2 methods that I'm going to discuss is that the natural impedance of a zigzag transformer is quite high. So it only has a low impedance when it comes to 0 sequence currents. And you can see in the winding, the net flux in each core is 0 because they're balanced, or the coils are wound in opposite directions on each leg. You can use the same system by employing a Y-grounded delta method. And this resistor here is the same value as the voltage to neutral, the neutral voltage to ground impedance. So if you had a neutral available, and if the zigzag method, this resistor is exactly the same value. You can see here that the delta here creates a path, but the resistor limits the fault current. You can use a Y-grounded open corner delta. And if you use a Y-grounded open corner delta, a little bit more work has to be employed here. So if we had a 5 kV system and you wanted to limit the fault current to 5 amps of a fault here, let's say we wanted to limit this current to 5 amps, on a 4160 to 120 volt PT, so you can see that these ratios here, 4160 to 120, we develop, when we have a ground fault, the current goes down through the fault and back to the source, and we complete the circuit this way. So this resistor, when there's a fault on the system, is going to have a potential of 208 volts across it, if it's 4160 to 120. The current is the turns ratio times the fault current. So it's basically 34.67 times 5 amps, which gives us a maximum current of 57.9 ohms. And you divide 208 by 57.9, a 3.6 ohm resistor here will limit the fault current to 5 amps on the primary. For a low resistance grounded system, because we get many calls for people stating .2 times 2000 is a 400 amp fault rating. So then we have to choose a value greater than that to limit the current to, in case you have high impedance faults, because we don't want the resistor to get hot and perhaps burn up. On the system on a distributed neutral. So here's our distributed neutral. But we have to monitor the neutral. If it becomes grounded downstream, that must be detectable and tripped. If there's obviously if there's a fault on any phase, we have to detect that and trip immediately. A high resistance grounded system with a distributed neutral cannot be sustained on the system, so it has to be tripped right away. The reason for that basically is because this neutral point is going to elevate. You also have to monitor the integrity of the resistor here. The resistor becomes open circuited, or if the connection of the transformer to the resistor becomes short circuited, that must be detected and so we basically have a relay that does all this, and it's called the Sigma relay for so we discussed briefly. When we had parallel sources, you can see here that if you had a 5 on each one of these generators, your maximum fault current, if all 4 generators are running, 20 amps, and you have to trip. You can't keep that system running. If you have replaced these resistors with a zigzag transformer resistor on the zigzag and on the system, and you can maintain the system operational. Now, trying not to go over the time. Maybe Jessica can read a couple of questions, but we are going to take all the questions that we've been asked, and we're going to release them to you. Jessica, do you know what format that's going to be in?
Hi, Sergio. Yeah, so we have a recording of this webinar that we will be uploading on our website, www.i-gard.com. And if you go under the video and webinar tab, you'll find a whole bunch of webinars archived, including this one, so you'll be able to reference that. And then next Tuesday, we have the complimentary technical bulletin being released, also on this topic. So that'll reiterate a lot of key points that we went over today and hopefully answer more questions then.
All right, so that concludes the webinar. Be safe in this troubled time that we're in right now, and enjoy working at home and isolated.
Sergio, we only had maybe one or two questions? I can read them to you quickly if you have a moment.
Sure.
There's one question about whether the KV was hold on here, I'm just trying to find it. How about the impact on the sizing due to 80% higher VDF loads?
Sorry, VFD, you mean?
Sorry, I just read it how it was written. Let me take a look again. How about the impact on the sizing due to 80% or higher VFD loads?
VFD loads. When you have a lot of variable frequency drives on your systems, a lot of variable frequency drive manufacturers put capacitors on the front end of their to get rid of pulse width modulation frequencies. So when you have a lot of variable frequency drives, you have to account for the increase in capacitive charging current, because there's going to be an increase in capacitive charging current due to the implementation of the capacitors, and it's going to increase your capacitive coupling. But let me see if I can find that question and see.
If it helps, it's the second question from the bottom.
Yeah, I'm just trying to find it. The other thing you have to worry about is variable frequency drives. Is a variable frequency drive is not an isolation device. It's not a power source. So if you have a ground fault on the motor of a variable frequency drive, so it's on the output of the drive, that fault current is going to return back through the neutral grounding resistor on the transformer. But the frequency is going to be proportional to the output of the variable frequency drive. If you were running 50% speed, your voltage is going to be reduced 50% because you have to maintain the volt step. The frequency is going to be at 30 hertz. So you have to be able to detect that. We have systems that can detect that because we monitor, and all three phases contribute to that load, that fault. Because when you rectify to DC, that DC portion on the variable frequency drive is going to be 1/3 of A phase, 1/3 of B phase, and 1/3 of C phase for every cycle. And I've got a presentation that shows that, and I can actually show it to you very quickly here. Just bear with me. If you have a fault on the DC bus, first of all, it's highly unlikely that you're going to get a fault on the DC bus, but I'll show you what happens. If you can.
While you're pulling that up, Sergio, I will just tell all the attendees that this is the first webinar of our new webinar series. So like I said, we have the technical bulletin coming out next week, and then the following Tuesday, we have another webinar coming out. So be sure to register for that. If you have a copy of the invitation, it should be in your email mailbox. If not, check out our LinkedIn page. If you just search I-Gard Corporation on LinkedIn, you can find the PDF with all the registration links, the topics, and where you can find the technical bulletins when they are released.
All right, so if you look at your screen right now, we have a three-phase system with a single VFD on it. So what we can see is when you have a fault, the diodes are forward biased only when the voltage on A phase here, sorry, you can see that the diodes 6 and 1 are forward biased in this situation, so that we conduct, and the positive bus on A phase is actually the C phase portion here, right here. And diode 1 and 6 is B phase. So B phase is because it's a maximum negative voltage here, and A phase. 30 degrees later, it's the same, 6 and 1. So when we get to the next part of the sinusoidal wave, A phase is going to be the positive peak. B phase is going to be the negative. So you can see that it's not a separately derived source. So if you have a fault on the DC bus, what's going to happen is going to be part of A phase that's faulted, part of B phase that's faulted, and part of C phase that's faulted, 1/3 of the 60 cycle frequency. So you have to be prepared to know what percentage of current to put on the rating to put on your resistor for that to be in effect. But the most important thing is to detect that type of a fault, and it's very simple to do. That I don't know if that made things clearer or confused them even more, but it'll be clear in the handouts next week.
That's great, thank you. Another question here, is the test kV voltage AC or DC?
AC. It's a dielectric strength test. So we use AC.
Okay, how do you, sorry, go ahead.
I wasn't going to say anything.
How do you determine the charging current?
We can do it if you have a cable schedule and load distribution on your system. So we can actually calculate what your charging current is on the system. If you have an ungrounded system, it's very simple to calculate or measure the capacitive charging current because you can actually place a fault to ground. Theoretically, you should not have any problems when you do this. There are safe ways of doing it. And I think we have an application guide on our website that explains how to do this and what instruments you need to do this. But if you put a fault on your system with an ungrounded system, where the fault is, and if you measure that current, that will be your capacitive charging current of what you have connected to the load at that particular time. So it's only going to measure the capacitive current of the connected load at that time. If you have a resistance grounded system and you do the same thing, you put a fault on one of the phases, the fault current squared minus the resistive current squared, these things are all measurable, the square root of those two differences will give you the capacitive charging current. So let's see if I can write that down. 3IC0 is equal to the square root of IF squared minus, oh, I went off the page, minus IR squared. So it can be done. We've done it. You can't do this on a solidly grounded system unless you disconnect the solidly grounded system, convert it to a resistance grounded system or ungrounded system, and then measure the current at that time, and then put your ground fault back on, and then put the solid link back on. We've converted many systems from solidly grounded to resistance grounded strictly as an arc flash mitigation technique, and I think there's a webinar coming up in the future for that. And what people have found is that when they converted from a solidly grounded system to a resistance grounded system, their equipment repair costs reduced drastically. Because you have to keep in mind that up to 98% of all faults begin as single phase to ground faults, and then they propagate to a phase-to-phase fault. And as an arc flash mitigation system, we can actually reduce that, because a high resistance grounded system will limit the fault current to such a low level that it will not propagate to a phase-to-phase fault.
Okay, I think we have time for maybe one more question. Sergio, is resistor monitoring going to be required for all HRG systems, or just those feeding mobile or movable systems?
From my understanding, it's going to be required on all resistance grounded systems. They don't limit it to portable devices, mobile devices, high resistance grounding, low resistance grounding. It's going to be required on everything as per the Canadian Electrical Code. It's been in the mining code for a long time, but now it's in all resistors.
Okay, great, thank you. I think that wraps us up for time. We're pretty close to finishing here. So like I said, I'm still getting a few questions about when this is going to be available. We will get it on our website under the videos and webinar tab as soon as possible, so you can rewatch it and stream it then whenever you'd like, probably within the next 24 hours. And
the other thing I'd like to add is, I don't know how long this environment is going to last. So if there's something specifically you want to have done in this forum, please email support@igard.com, and we'll see what we can do to accommodate.
Yeah, absolutely. They'll be happy to help you with any specific system needs that you have. Okay, anything else, Sergio, or are we good to disconnect?
I'm good.
All right, thanks for attending, everybody. We will connect more next Tuesday and every Tuesday after that for the next couple months.